This lesson looks at evaluating the Solow growth model with labor augmenting technology. So I wrote a few extra notes here to remind us because this is really the only special case I consider in this course. So I modified our key result. This is still our key metric, GDP per capita. I'm just going to use the formula of GDP per worker to emphasize that this definition is different from this, because when we add labor augmenting technology, we get an E multiplied by the L, and we scale everything by dividing through by EL. So the growth rate of this is different from the growth rate of this, and this is still our goal. GDP per person in the economy, which we're going to call L and assume it in population the same. The other assumptions are that there's no other exogenous technological growth in this model. So A is not growing, A hat's just 0. There's no population growth occurring in this model. So N, the population, is growing at 0, which means labor is growing at 0. This is what makes the model a little different. This E, which is the efficiency of labor, is going to be assumed to grow, and it's coming through some kind of technology at a rate of G that's greater than 0. So the technology is growing again at a constant rate, which is kind of a backdoor cheat way of getting back to exogenous tech growth. But we're going to assume it grows. It's specific to labor, so it does enter everything a little differently. If you remember these things, I've denoted them by little e just to keep them different from what's divided just by L as we normally do it. The rest basically is the same. Step 1 is to use the definition of steady state in this model. So we're using this in steady state. And so in this model, it is this being constant. So that's the definition of steady state, not this being constant, which is just a normal K. So we use the definition of KE, which is right here. We convert into growth rates. You could think of this as E plus L, all minus L hat. Now, the definition of this is that this whole thing has to be 0. Okay? That's the definition of steady state. So I know this. Also, because we assume no population growth, we know that is 0. Additionally, I know that gives this growing at GE. So K hat minus E hat has to equal 0. This is GE, so it tells us that K hat minus GE has to equal to 0, which is the same as saying K is growing at a rate of GE, which means the total stock of capital must be growing at the same rate as technological progress here. Again, if I wanted to plot L, it's constant. If I wanted to plot K, it's growing at GE. If I wanted to plot E, it's also growing at GE. And of course, those are all logs. And so is that. Okay, fine. All of those together mean this divided by that and that. Because this one's growing, those two divided by each other are going to mean this is constant, which is why its steady state level is 0. Step 2 is to look at production. Now again, don't forget, we're looking at YE. So when I convert this to hats or growth rates, this is 0. And this is 0 by definition here. So let me use green here. That is 0, and this is 0 by definition. So y hat e is 0. Looks a lot like the original Solow model. This is where the trick comes in. We're not evaluating this, we're evaluating that. This ye is y over el. When you convert it to hats, you get y hat minus e hat minus l hat. We're going to get this thing growing just like this. That's 0. We know this thing's growing at 0. We know this thing's growing at g, so we know y hat is growing at a rate of ge. Log. But our goal is not this, it is to get GDP per worker, period. That we now know. This is growing at GE. This is growing at 0. So let's use red. We've got total GDP growing at a constant rate, and so GDP divided by a constant workforce is also growing in this model with labor augmented technology.